so this is a recap. We talked about equilibrium, and we've been saying all along. So this is notes. This is new stuff. We've been saying all along, if it's not moving on that axis, sum of forces equals 0. Yeah. Oh, okay. Well, let's talk about equilibrium now. Thank you. I do need somebody to keep me in line. You're hired. This is okay, we've been doing this without having formalized it. So every single time we look at an object and we say, is it moving? Is it accelerating? If it's not moving or it's moving at constant velocity, sum of forces on that axis is 0. Why is that? Well, force equals mass times acceleration. If that's 0, then the net, and this is, by the way, net force, then the net force is equal to 0 if it's not accelerating. It could be either at rest or it could be moving with constant velocity. So we've kind of been doing this, though we haven't formally discussed it. This is what you've been doing. You know, how do we know something is at equilibrium? Well, the first way is we ask ourselves the question, is it moving, is it accelerating? And then, you know, that's on each axis, which is what we've been doing. Well, then, if all the forces are 0 on both axes, then the total sum of all forces on it is 0, and it's at equilibrium. If you're driving down the road, straight road on cruise control, equilibrium? Yeah. You know, with certain little foibles and bobbles of inconsistency, but yeah. So this is what we've been doing. Well, now we're going to start to talk. Okay, so what you've been doing has been resolving forces, resolving net force. Well, when we think about those net forces, we're getting towards the point where we start talking about the fact that force, net force, equals mass times acceleration. But to do that, we need to address a little sort of elephant in the room called inertia, which is that an object at rest tends to stay at rest, an object in motion tends to stay at motion. You've done that before. That's Newton's first law. Acceleration is proportional to mass. And so if we look at this, if we have a larger mass object, the same force will generate less acceleration in it. Inertia is proportional to mass. It takes more force to get heavy stuff moving than it does to get light stuff moving. Obviously, you haven't done it this winter or lack of winter. Who here has pushed a car out of snow? Okay. I'll push a Honda Civic ahead of a dump truck any day. It takes less force to get the smaller thing moving. Now, let's talk about inertial braking systems. Who here has ziplined? Just one of you? Okay, we need to fix, two of you. We need to fix that. There is actually a mini zipline at the Carnegie Science Center in the Sportsworks complex. And it's like a high ropes course thing, and then you zipline part of it, and my daughter and I enjoy doing it. And on the zipline component, at the end of the zip line, so you come off this platform and you land on this platform, and right about here, not in the path of the zip liner, but sort of off to the side, is this big black box. And inside the big black box, you're looking at the flat surface of it. There is a little panel, and that little panel has got a visible spot. I guess I didn't do as good a job of that as I thought I did. And that spot it's an opening to the thing behind it, and that spot is either green or red. Guess what that means? If it's red, you're not supposed to zip line. It has to be green for you to zip line. So that black box is actually hollow. And inside that black box, what you can't see is that there is a massive weight. And the green and the red spot are just a hole in the cover that exposes a different part of the weight. That weight is on a cable going up through the covering, and that is connected to basically a peg that you hit on the Zipline. Now, I'm ashamed to admit that as a physics teacher, the first time I saw it, I'm standing there looking at it and going, how does it work? How does it work? How does it work? It took me 3 trips up to totally get it. But that's okay. I can get up to 4 kids under 18 in if anybody wants to meet me on a Saturday. I've got 1. I can get 3 of you in for free. And if any of you are 18, I can get you in as an adult. So anyway, field trip. When you hit this weight, you take that and you push it forward. And that's connected to a line that pulls that weight up. When that weight goes up, it's stopping you. Now, my daughter, who weighs like 80 pounds, hits that thing and man, does she stop. You know, and I watched some little tiny kid, and I wasn't sure that the kid was going to like get onto the platform because the kid hit it and the weight just went whoop. I hit it and that puppy goes up. I'm going to guess that that weight is at least 500 pounds of, you know, metal. It's heavy, and they let grown-ups on it, and they want to make darn sure you stop. This is an inertial braking system. What is braking you is the inertia of that mass, because that mass doesn't want to move. But your body on that cable hitting the other end of the rope for the weight essentially pulls that weight up, and the inertia of the rope stops you. Years ago, we were dating, but my husband and I, then boyfriend, went ziplining in Southeast Ohio, and we did the super zip. And it's like a 1-mile zip line. You come off this platform, you go over a lake, you come into this little, well, the stop cage. And they say in big letters everywhere, maximum weight 250. So we get up to the top, and they don't do, I mean, like on bungee jumping, there is a scale, and they will write your weight on your arm. Shame be damned, our insurance can't afford you to die. On this, they just, you know, and like my little tiny friend Kimmy, they're like, okay, if you want to speed up, just go like this. If you want to slow down, go like this. They took one look at my husband and said, okay, buddy, what do you weigh? And he said, 275. Because they knew, I mean, looking at him, you could tell he was clearly, if not over 250, he was real close. And they said, okay, we're going to give you the scoop. And he literally had to wear an apron that had a wind scoop on it. And, you know, he had told little Miss Kimmy, like, you can speed up by going like this. And he looks at my husband and goes, dude, you're going to spread out as big as you can. Well, it's an inertial braking system on the end. And the first weekend they had opened, they had somebody go up who was like over 300 pounds and said, no, I'm not over 250. You're dependent for stopping on the weight on the other end of the inertial braking system. Now, after that incident where someone nearly died because that individual didn't stop when they were supposed to, and there's a wall at the end, and you build up a heck of a lot of velocity over a 5,000-foot zip line. So they got a little bit more serious about going, what do you weigh? What do you weigh? But I think they did increase the mass on their inertial braking system also. You know, it matters. If you weigh less than that inertial brake, you're not stopping. So maybe we should do a field trip to the Carnegie. It seems like an awful lot. No, I'm never planning a field trip again. Repeat after me, Moser. Okay. Questions on inertial braking? Reverse that. Moser's having a stupid week. If you weigh more than the inertial brake mass, you're not going to stop. If you weigh less than it, you're going to stop. You know, again, with like the little kids, if you weigh a fraction of what it weighs, you're going to wham! You're going to hit that thing and like hitting a brick wall. We've got one little kid on my DI team, I swear she weighed like 30 pounds. Every time, oh my God, she's adorable. And every time I go to pick her up, because I'm used to my kid who's really solid, like I go to pick her up and I'm like throwing her through the ceiling because she weighs nothing. But anyway, you know. That makes sense? Okay. If you hit that and you weigh the same as the mass, so you and that equilibrium brake, or that inertial brake, weigh the same, will it stop you? Yeah. Not fast. Maybe not in the time necessary. But if we put you, here's you, here's the inertial brake. If we put the two of you on one side of a pulley on a cable, you're going to balance. You have the same mass. What if we substitute for you, my little DI kid who weighs like 20 pounds? What's going to happen? She's going to go flying up through the pulley. Yeah, she's going to have a rapid acceleration upwards. What if we put some sort of elephantine creature? There, some sort of elephantine creature on that. Pulley's going to go flying up. So, you know, at the point of equilibrium, forces are balanced, things are not going to be accelerating. We will stop there. What we're going to do tomorrow is start to introduce some problems where things are not at equilibrium. But tomorrow we're going to start working with objects. Up till now, everything that we've done has been at equilibrium. We just didn't talk about it. Or we were able to assume it at least on one axis that it was at equilibrium. Here we're going to start examining situations where there is acceleration. So that's it.